Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 17, 2025, exactly a week ago. This paper's key finding is that the long-standing Gallium Anomaly, a puzzle in particle physics, has now intensified to a 6.1 sigma discrepancy. The paper is titled, Reassessing the Gallium Anomaly Using Exact Electron Wave Functions, and as we'll see, this result strengthens the case for potential new physics. The anomaly itself is a persistent difference between theoretical predictions and actual measurements in key neutrino experiments. Alright, so the key to this updated analysis is a much more precise calculation of the neutrino capture cross-section. That's a term for the probability of this specific reaction happening. This first figure visualizes the core of the new method. We're looking at different properties versus the distance from the center of a germanium-71 atom's nucleus. The blue line shows the Fermi function, which is a crucial correction factor that accounts for how the nucleus's positive charge affects the electron emitted during the reaction. Notice how it changes with distance, which is precisely why a simple single-point assumption isn't enough. This next table quantifies that very effect. It compares the older standard calculation of the Fermi function to the new methods for the chromium-51 and argon-37 neutrino sources. The key result is in the final column, which shows the Fermi function averaged across the whole nucleus, not just at a single point. You can see these average values are consistently lower. This adjustment might seem small, but it reduces the overall theoretical prediction for the reaction rate by about 3.3%, making the measured anomaly even more significant. So with that refined theoretical prediction in hand, this figure brings it all together. It plots the ratio of the actual experimental counts to the new theoretical prediction. A perfect match would be a ratio of 1, but you can see all the experimental results fall significantly below that. The top panel, using one method for calculating contributions from nuclear excited states, shows the combined result is a 6.1 sigma anomaly. A sigma value measures statistical significance, and 6.1 is extremely high, suggesting this isn't a random fluke, but a real persistent discrepancy. So what could be causing this discrepancy? One leading hypothesis is a new, undiscovered particle, a sterile neutrino. This is a hypothetical fourth type of neutrino that doesn't interact like the others. This final figure explores that possibility. The red and purple ovals show the properties a sterile neutrino would need to have to explain the gallium results. The key property is the mixing, basically how often a regular neutrino turns into a sterile one. But the cyan and green lines show the limits from other major experiments. The problem is, the regions that explain the gallium anomaly are ruled out by these other results. This tension is what makes the puzzle so compelling. So, in conclusion, what we have is a classic scientific puzzle. The authors have presented a much more precise calculation for the neutrino capture cross-section, and by doing so, they've shown that the gallium anomaly is not only real, but even stronger than we thought, now standing at a massive 6.1 sigma discrepancy. While the sterile neutrino offers a tantalizing explanation, it remains in conflict with other key experiments. This work really solidifies the anomaly as a major unsolved problem in particle physics. That's all for this week's AI Research Roundup. Thanks for tuning in.